Hello everyone. Welcome to our course on AVEVA E3D 4.0 in Unified Engineering. In this, we'll start with the fundamentals, then explore how equipment can be modeled in E3D using different methods. Let's begin with the fundamentals. Unified Engineering is the overall platform that combines 1D, 2D, and 3D engineering data into one space. 1D covers datasheets and lists. 2D covers schematics such as P and IDs and instrumentation diagrams. 3D is the design environment, where plant models and equipment are handled. In the app, you'll see a list of projects that are available. For this demonstration, we'll choose a project called Proj APS. Alongside the main project, you may also see reference projects such as ACP, PSL, and CPL. After selecting a project, under Setup, you will enter a username and password specific to that project. These credentials define what you can do inside the project, whether you can read or write to the database, and which modules you can access. At this stage, you'll also select your scope. A scope is a collection of databases that work together to give you access to different parts of the project. For this course, we'll choose the scope All. Now, just above the setup, you'll see the list of modules available under this project. On the 3D side, which will be the main focus of this course, you'll be working with several modules. Model, for 3D modeling. Draw, for creating 2D drawings. Isodraft, for producing isometric drawings. Spool, for generating spools from your modeled pipework. Paragon, for catalogs and specifications of component-driven items in the model. PropCon, for defining properties of those components. You also have Engineer and Engineer Config modules, which support 1D and 2D. For now, we'll begin with the Model module. Let's take a look at the E3D Design Model interface. At the very top left of the screen, you'll see the Quick Access toolbar. Below this, you will see the ribbon. The ribbon is organized into tabs and groups, with each tab containing a set of related commands. The middle of the screen is your viewing area. This is where your 3D model will appear and where you'll do most of your work. On either side of the viewing area, you can have what are called sliding forms. For example, let's open the Model Explorer. The Model Explorer is your way of browsing the project database, things like sites, zones, and elements. Now let's look at the right side. If I select an item in the model and choose to view its attributes, you'll see the attribute form appear on the right. If I don't need it, I can collapse it to free up more workspace. At the bottom of the screen, you'll see the notification area on the left, the message area in the middle, and the status bar on the right. And finally, within the viewing area itself, you'll notice a small navigation tool called the Power Compass. By default, it usually appears near the bottom, but you can drag it anywhere you like. We will move it to the top right since it keeps it out of the way while still being easy to use. One of the strengths of E3D is that you can customize the workspace to fit the way you like to work. Let's look at a few simple adjustments you can make. First, if you want the maximum viewing space, you can hide the sliding forms on the left or right as we previously discussed. Alternatively, you also have this clear canvas button near the top right corner which allows you to hide all open forms. Clicking the button again will bring the forms back. Next, the Power Compass can be configured to match user preferences. By default, it controls the orientation of the view, but the behavior can be adjusted. For example, the compass can be set to look north rather than look from north, changing how the model reorients when the north button is clicked. The size of the compass can also be customized, either kept large for visibility or reduced to occupy less screen space. The sliding forms themselves can also be divided. On the left, the panel can be split into two sections, which allows, for example, the Model Explorer to remain open in one section while another tool is used in the other. We can open another Explorer panel to see what this setup would look like. The same applies to the right side, where we could display, for example, a command window next to the attributes form. For multi-monitor setups, forms are not restricted to the main application window. They can be undocked and floated onto a second screen, keeping the 3D workspace clear on the primary monitor. You can also float the entire form area, which can have multiple forms within it. Finally, right-clicking inside the viewing area opens the power wheel. This context-sensitive menu changes depending on the element selected, and provides quick access to navigation and editing tools directly within the model space. Next, let's look at the toolbars and disciplines. At the very top of the screen is the Quick Access toolbar. This bar holds commonly used commands and can be customized to match your workflow. For example, if there's a tool that is used frequently, such as search, it can be added directly to the Quick Access toolbar with a simple right-click and Add to Quick Access toolbar. Below that sits the ribbon, which is divided into tabs. Each tab groups together commands related to a specific type of task. In addition, you also have discipline workspaces. Changing the discipline changes the tabs that are shown in the ribbon. For example, if the equipment workspace is selected, an extra tab appears with commands for equipment modeling. If you switch to piping or structures, you'll see tabs with tools specific to those disciplines. Next, let's explore how the Model Explorer connects with the 3D workspace. The Model Explorer provides a database view of the project. From here, elements such as sites, zones, or individual items can be browsed and selected. To bring an element into the 3D view, there are a couple of options. Under the View tab in the ribbon, the Add C command can be used to display the current element. Alternatively, elements can simply be dragged and dropped from the Model Explorer into the 3D workspace. Remember that to maximize the modeling area, the Clear Canvas button in the corner of the screen can be used, giving us more space to work on the model. Once elements are in the view, navigation is handled using the mouse. Pan by holding the middle mouse button along with the control key and then move the mouse. Zoom by scrolling the mouse wheel forwards or backwards. The zoom is always centered around the position of your cursor, so if you move the cursor to a different part of the screen, the zoom will focus on that area instead. Rotate by pressing and dragging the middle mouse button while hovering over a point of interest. Notice that the center of rotation depends on where the cursor is placed. If the cursor is positioned over an object and the view is rotated, that object becomes the pivot point. If the cursor is in empty space, the view rotates around the general model area. This makes navigation intuitive and keeps the area of interest in focus. Another important concept is the current element, C. Whenever something is selected in the Model Explorer, that item becomes the current element. The same applies in reverse. When something is selected directly in the 3D view, using the left mouse button, the Model Explorer highlights it as the current element. The Explorer will follow the item that you've selected in the 3D view. Now that we've looked at how to navigate using the mouse, let's explore two additional tools that make working in the 3D view faster: the power wheel and the power compass. Right-clicking inside the viewing area brings up the power wheel. When you select an element, the wheel adds commands specific to that object. One very useful option here is center view, which quickly shifts the camera so the chosen item is brought in the center of the view. The power compass gives directional control of the view. For example, clicking on north aligns the model to look north, while clicking down aligns the view to look down. Other options are also available depending on the perspective needed, and the compass makes it easy to switch between them quickly. Below the compass are small left and right arrows. These allow cycling through previous and next views, much like moving backward and forward in a web browser. It's an efficient way to revisit earlier viewpoints without manually rotating or repositioning. You can also create multiple views inside your workspace. Under the View tab, the option Copy to Clone View creates another view with the same content as the current one. Any changes made in one clone view are reflected in the other. For example, if we create a new vertical tab group and add in the pipe rack from the structures, it appears in the clone view as well. Next, Copy to Separate View creates a new view that looks the same at first, but is independent. Let's create a horizontal grouping for the separate view. If we now remove an element in the separate view, you'll see that the element remains visible in the original. There is also an option to copy a local view. To demonstrate, let's select 3 items. Multiple items can be selected by holding down the Control key and left-clicking. When we copy these into a local view, only the selected items are displayed. Now let's move this local view into a horizontal tab group with the original view. Note that views can be moved between groups by right-clicking on the tab and choosing where to place them. Now that we're familiar with the basics of logging in, exploring the interface, customizing the workspace, and navigating the 3D environment, let's move on to equipment modeling. Let's start by creating a simple equipment using primitives and catalog components, which is one of the ways to model equipment in E3D. Along the way, we'll explore key concepts like elements, attributes, and representation levels, which define how equipment is built and displayed. Before we start modeling equipment, it's important to understand how data is organized in E3D. On the left-hand side of the screen, we have the Model Explorer. Every item you see in this tree is called an element. Elements are the basic building blocks of a project, and each one carries its own set of attributes. Let's take an example. At the top, you'll usually find a site. A site is a type of element. Inside a site, we have one or more zones. A zone is also a type of element, and this is where equipment gets created. In other words, equipment always belongs to a zone, and that zone belongs to a site. Now, every element comes with attributes such as position and orientation. These values define the local coordinate system for that element. So, a site has its own position and orientation. A zone inside that site also has its own position and orientation, but it is defined relative to the site. An equipment under that zone has its own position and orientation, relative to the zone. This hierarchy is what ensures that everything in the project lines up correctly. Let's look at this more closely. If I open the attributes form for a site, you'll see basic fields like its name, function, and description. You'll also see the position and orientation fields. These are especially important because they act as the reference system for everything placed within that site. The same applies to zones and equipment themselves. Each one has its own position and orientation values. This means the whole model is built up step by step, with each element sitting in the right place because of the attributes it inherits and defines. When modeling in E3D, two concepts you'll come across often are obstruction and representation levels. These affect how elements interact with each other and how they appear in the 3D view. Every primitive has an obstruction setting. If it's set to 2, the primitive participates in a hard obstruction check. If it's set to 1, it participates in a soft obstruction check. And if it's set to 0, the primitive is ignored in obstruction checking. This means the software can tell whether elements clash with each other, and whether that clash is hard, soft, or not checked at all. Next is the representation level, which controls whether or not a primitive is displayed in the current graphical view. Let's open the Graphics Drawlist form. Here, you'll see the different levels available for display. Right now, the drawlist is set to level 6. That means only primitives whose attributes include level 6 are visible. For example, if a primitive is defined with levels from 0 through 8, it will appear, because 6 falls within that range. Now let's change the drawlist to level 9. You'll notice that some of the equipment disappears, and other items become visible. This is because their attributes are defined to include level 9 instead of level 6. To confirm this, let's select one of the items that just appeared and open its attributes form. Here you can see its level set between 8 and 10, which explains why it shows up at level 9 but not at level 6. In the same form, we can also see its obstruction value as 1, which determines how it participates in clash checks. This combination of obstruction values and representation levels gives you control over both the accuracy of clash detection and the clarity of what is shown on screen. For example, you can work with a simplified view when modeling, and then switch to a more detailed view to check surface areas or additional geometry. We can also control how obstructions are displayed using obstruction visibility or translucency settings. Let's take the cylinder inside equipment D1201 as an example. If we look at its attributes, its representation level is set from 0 to 8. Since our graphics drawlist is currently set to level 9, the cylinder doesn't appear in the view. However, if we adjust the obstruction visibility from off to, say, 75%, the cylinder now becomes partially visible. This is because its obstruction value is set to 2, meaning it participates in hard obstruction checks and can be displayed as translucent. If the obstruction value had been set differently, for example, to 0, then even with visibility at 75%, the cylinder would not be displayed at all. I have cleaned up the view by removing all items, and now that we understand how elements, attributes, and representation work, let's put it all together and create our first piece of equipment. We'll begin by creating a new site. We'll call this TDS site. Next, we will create a new zone and call it TDS zone. Think of the zone as a container. It's where we place the equipment for a specific area of the project. Once the zone is created, we can add our equipment into it. Inside the zone, let's create a new equipment element reboiler. As soon as we click the equipment button in the Create group, the equipment creation form appears. This form allows us to specify exactly where the equipment should be placed in the 3D space. For now, let's place it at the origin point 0, 0, 0. We'll also give this equipment a name, TDS 1301. With the equipment element in place, we can now build up its shape using primitives. Primitives are simple geometric forms, cylinders, cones, spheres, and so on, that combine to form the body of the equipment. Let's start with a cylinder, which will represent the main body of our tank. First, we go into the View ribbon and set the coordinate system to EU. This ensures that the cylinder is created with the correct orientation. Next, we create the cylinder itself. We begin by selecting the center point. Then we enter the diameter, which we set as 835 mm. Finally, we specify the height. This gives us the overall body cylinder of the reboiler. Next, we'll create a few cylindrical plates for our reboiler. A cylinder can be created either through the user interface, or by typing CYLI directly in the viewing area. For the first plate, let's position a cylinder at one side of the main body. We'll set its diameter to 960 mm and its height to 60 mm. Once that's done, we'll create additional copies. With the first cylinder selected, we enter the copy command in the view. We choose a base point on the original cylinder, and then place 3 copies. One 640 mm away, another at the opposite end, and a third placed right next to it. This gives us 3 new cylinders in addition to the original, forming the plates we need. For the third plate that we created, let's make a few adjustments. First, we make sure the plate is selected. Then, we'll reduce its diameter slightly to make it narrower. We'll also adjust the length of the plate, so it's longer than the others. Next, we'll add a dish to this end of the reboiler. From the Create group in the ribbon, we select the dish option. We then set the base point of the dish at the center of the cylinder we just extended. After that, we match the diameter of the dish to the cylinder, so it fits seamlessly. Finally, we define the height of the dish. With that, the dish is now added to the model. Let's go ahead and create a sub-equipment. To do this, we go to the Create panel, and under Equipment, select Sub-Equipment. This new element will sit under the main equipment we're working on, and it can contain multiple primitives. For now, we'll just add a single box. We begin by specifying one corner of the box, and then define the opposite corner to set its size. With that, the box is created as part of our sub-equipment. Next, we'll make a copy of this sub-equipment. First, we ensure the sub-equipment is selected. We can do this using the power wheel. Once it's highlighted, we run the copy command. Next, we choose a base point on the original sub-equipment. We then specify the new position. Finally, we place the copy in the new location. This gives us another instance of the same sub-equipment. Now, let's create a nozzle. First, we go to the equipment level. Then, in the Create group, we click on the Nozzle button. This brings up the nozzle creation form. In this form, we'll give the nozzle a name, TDS 1301/NS2. It's generally recommended to name nozzles with the equipment tag as a prefix, so we've followed that convention here. For this example, we'll use 150 pounds ANSI flanges as the specification. We'll keep the bore size to 150 mm. Additionally, we'll set height to 635 mm. Clicking Create generates the nozzle and opens the Modify Nozzle form. At this point, we still need to adjust its position and orientation. We begin by changing the position. Then, under Rotate, we rotate the nozzle 90 degrees about the y-axis. Once that's done, the nozzle is in the correct place and orientation. Next, we want to create a copy of this nozzle, rotated 180 degrees. We begin by selecting the newly created nozzle. Then, we type in the command RO. For the base point, we select the base of the nozzle. After that, we rotate it 180 degrees. With that, we now have a second nozzle, copied and positioned opposite the first one. Now let's update the name of the newly created nozzle. We open the Modify Nozzle form from the Modify group. In the form, we change the name to TDS 1301/NS1. Once that's entered, we click Next to apply the change. Next, let's copy the nozzle NS2 to another location. We'll use the Move command with the Copy option enabled. First, we select the base point on the original nozzle. Then, we set the new position along the reboiler's body. For this copy, we'll place it 835 mm away from the original. This gives us another nozzle correctly positioned along the equipment. Let's now modify the newly created nozzle. We open the Modify Nozzle form. First, we update the name to TDS 1301/N2. Next, we change the type to 300 pounds ANSI flanges and set the bore size to 300 mm. Once those changes are made, we click Next to confirm. The nozzle is now updated with its new properties. Next, we'll create two copies of this larger nozzle. We'll use the Move command and then select the Copy option, just as we've done previously. First, we select a base point on the nozzle. Then, we copy it 2,440 mm along the reboiler. We repeat the same process again, this time placing the copy 4,880 mm along the reboiler. With that, we now have two additional nozzles positioned along the reboiler. We'll now rotate the middle nozzle out of the three larger ones. To do this, we use the RO command. We choose a base point on the nozzle, and then rotate it 180 degrees. This flips the nozzle to face the opposite direction. Now, for the two nozzles we copied, we need to update their names. We begin by opening the Modify Nozzle form and selecting the middle nozzle. In the Name field, we enter TDS 1301/N1, and then click Next to confirm the change. The nozzle is now renamed and properly labeled. Next, we select the corner nozzle and open its Modify Nozzle form. This time, we change the name to TDS 1301/N3. Once again, we confirm the change. By renaming these nozzles, we maintain a consistent naming convention across the reboiler. This is important because clear, unique identifiers make it much easier to track, reference, and document each nozzle. That wraps up our walkthrough on equipment modeling with primitives. We looked at how elements are structured in E3D, explored attributes like position and orientation, and saw how obstruction and representation levels affect what's displayed in the 3D view. Using these concepts, we built a simple reboiler model using primitives and nozzles. Next, we'll look at another way to model equipment, using templates. Templates allow you to create equipment more efficiently by using parameterized components that have been predefined by the administrator and organized into suitable categories and subcategories for easy selection. Once a component is selected, its key dimensions can be adjusted to match your design requirements. This is the form used to select and create equipment from templates. Here, you can choose the appropriate selection table and specification, which define the library and standard used for the equipment. The items are grouped under specific types, for example, heat exchangers in this case, and each template is listed with its item name, part type, and description. Once you've selected the desired template, a 3D preview appears at the bottom of the form. You can then click Apply to create the equipment in your model. Now that we understand the process, let's create a heat exchanger using the equipment template. To begin, go to the Equipment ribbon. Under the Create tab, select Create Standard Equipment. Next, we'll fill in the details in the Create Equipment form. The first field to define is the name of the equipment we are creating. You can either enter a custom name or use the Auto Name option, which is predefined by the administrator. The Auto Name system automatically generates a name based on the project's naming rules or conditions. If you prefer, you can leave the name field empty for now and define it later after the equipment is created. Keep in mind that the name must be unique, as E3D needs all names for the elements to be unique. The next step is to select the equipment template library that we want to use. The library defines the collection of available templates and how they are organized. In E3D, there are two common ways this library can be structured. Selection table, a simpler structure that contains a single level of subcategory. Specification, a more advanced setup that supports multiple levels of subcategories, allowing templates to be organized in greater detail. Depending on how your project or administrator has configured the system, you may see either or both of these options available for selection. By selecting a series of options, you will gradually filter down to the list of templates that meet those criteria. Each selection narrows the choices until the available templates are displayed. After narrowing down our choices, we can now see 4 available templates that match our selection criteria. Once a template is selected, we can define its associated properties. This opens the Modify Properties window, where we can adjust key parameters such as the flange diameter, exchanger diameter, flange thickness, head height, and exchanger length. For this demonstration, we'll keep most of the values at their defaults, but we'll update 2 parameters. We'll set the flange diameter to 2,200 mm and the exchanger diameter to 2,000 mm. Once we're done, we click OK to confirm the properties, and then click Apply to create the equipment. The system will now ask us to define the position of the exchanger in 3D space. We'll ensure that the coordinates are 0, 0, 0, to that we can place it right at the origin point. Now that we've positioned the exchanger at the origin, let's take a look at it in the 3D viewer. We can orbit around to inspect the model from different angles, and as you can see, the exchanger has been created automatically using the template we selected. It already includes all the main components, the shell, the 2 end heads, and the flanges on both sides. Some templates may even include basic nozzles or supports, depending on the configuration. Now, let's see how we can modify this exchanger. From the Equipment tab, under the Modify group, we click on Standard. This opens the Modify Equipment Specification form. From here, we can access the properties again and change some of the parameters we set earlier. In this case, let's reset the values for the flange diameter and exchanger diameter back to 1,200 mm and 1,000 mm, respectively, the same dimensions we used before. Once we click OK, the geometry in the viewer updates instantly to reflect the new settings. This flexibility makes templates extremely useful for making quick design adjustments without rebuilding the equipment from scratch. Now, let's look at how we can remove one of the optional components, for example, the supports. From the Equipment tab, we open the Modify Template form. In the Modify Properties panel, there's a field called Exchanger Support, which is currently set to horizontal exchanger feet. If we don't want these supports, we simply change this option to No Supports. When we click OK, the box-shaped supports are removed from the model immediately. This is one of the advantages of templates. You can toggle optional parts on and off without deleting or remodeling anything manually. For now, let's add the supports back in. We set exchanger support to horizontal exchanger feet again and apply the change. The supports reappear beneath the exchanger. Because these supports are template-driven, we can also customize them. Click the small Properties button next to the exchanger support drop-down to open the detailed settings. Here, we can adjust parameters to match our project needs. And note the plot on the bottom. The callouts A, B, C and so on correspond to the property names in the list, making it easy to identify which dimension you're changing. Now that we've explored how to add and modify template supports, let's create our own custom supports instead. We'll start by creating a new sub-equipment under the exchanger and name it TDS Sub. This sub-equipment will hold our custom support shapes, keeping them organized and separate from the main exchanger. Inside TDS Sub, we'll add 2 boxes, one for each support location. The idea here is to create custom supports that have a tapered, trapezoidal shape instead of the flat box supports we used earlier. We'll first focus on the first box, which we'll later modify by cutting away a section using a negative primitive to give it that sloped profile. Once we've finalized its shape, we'll then copy it over to the second support position. For now, we're simply adding both boxes so that the second one acts as a placeholder. This will make it easier to snap and align the copied support later on. Additionally, we're removing the supports from the template since they are not needed anymore. We'll start with the first box. Our goal is to create a slanted cut across this box using a negative primitive, so the first step is to set up a local coordinate system for the cut. We'll move about 50 mm away from the base of the box, where we want the angled cut to begin. To define this new plane, we'll select 2 points out of the 3 required, both positioned 50 mm inward from the end of the box. The third point will be the top inner corner of the box, which sets the slope's orientation. Once these 3 points are selected, a local coordinate system appears, indicated by the letters on the power compass, confirming that our custom plane has been defined successfully. Next, we'll enable snapping to the local coordinate system so that our picks are projected onto the LCS plane we just defined. A quick note: negative primitives only appear when you're at the correct hierarchy level. So we'll first select the target box inside TDS Sub to make it the current element, and then create a negative box. We'll use the 4-point method to define this negative box. Point 1. Pick at the base, slightly below the support so the volume is easy to see. Point 2. Pick along the base to define the first edge. Point 3. Pick at the top to set the height of the cutting volume. Length. Enter -500 to extrude the negative box in the opposite direction of the LCS axis. After confirming, you'll see that a slice of the solid is removed. The cut follows the angled plane we defined with the LCS, giving the box its trapezoidal profile. Now that the cut is complete, let's switch back to the world coordinate system so that any further actions are aligned with the global axis. We'll also turn off Project Snaps onto LCS, since we no longer need our selections to be projected on the local plane. Next, we'll navigate to the modified box. We'll now copy this support to the other side. To do that, we'll run the copy command, then select the center of the box as the base point. We'll move the cursor over to the placeholder box we created earlier, and snap the copied box right into its position. Once the copy is in place, we can delete the placeholder box, leaving us with 2 identical, angled supports. Now we'll rotate the support so that it faces the correct direction. First, we'll make sure we're at the primitive level. Next, we'll enter the rotate command. We'll select the center of the box as the base point, and then specify a rotation of 180 degrees. Once we confirm, the support flips into its new orientation. With this, we've seen how templates can be used not just to create standard equipment, but also as a foundation for customization. By combining template-driven components with user-defined geometry, you can build flexible, project-specific designs quickly and efficiently. We've now completed the process of creating and customizing equipment using templates in E3D. Starting from template selection, we defined parameters, created the heat exchanger, explored its internal structure, and made modifications such as toggling supports and shaping them with negative primitives. Through this exercise, you can see how templates make equipment modeling faster, more consistent, and much easier to modify, all without rebuilding geometry from scratch. Next, we'll move on to the third way of creating equipment, using the standard model library. We've already set up a standard model library, so let's start by creating equipment from it and then walk through how that item was added to the library. Go to the General ribbon, and under the Create group, select Standard Model. This opens the Standard Model Library item form, shown on screen. Before we proceed, let's take a moment to understand the form layout. The storage zone defines where the new item will be created within the model hierarchy. The selection section includes drop-downs for library, library area, and standard model library items, listing all the entries available for use. Below that, the New Instance section allows you to define the name, orientation, and position of the new item before placing it in the model. Now we'll create a new instance from our library. The library and library area have already been selected, so in the items list, we'll simply choose the TDS heat exchanger. We'll assign it the name TDS 2001. If needed, the orientation can be adjusted in the section below. In our case, there's no need to make any changes, so we'll leave it as it is. Next, click Create and Position. You'll be prompted to select a point in the model. Choose a suitable location, typically somewhere appropriate within your modeling space. Since we're not working within a specific plant model here, we'll instead use explicit position and set the coordinates to 0, 0, 0, where the equipment's origin will be placed. The standard equipment now appears in the model, complete with its geometry and hierarchy intact. Now that we've seen how to add a component from the standard model library, that wraps up our first steps in E3D 4.0. You've learned the fundamentals of Unified Engineering 3D, or E3D 4.0. You should know how to move around the workspace, and how to model equipment using primitives, templates, and libraries. These are the basics you'll build on for everything that comes next. Thanks for watching, and if this helped you get started, don't forget to like and subscribe. We really appreciate your support.